So similar to AM modulation, here in the deduction also we have two different types of AM deduction. One is using a square law detector, and the other one is called as an envelope detector. Okay. So demodulation is a process of recovering the original message signal from the modulated waveform. So in both these detectors, we are going to pass the AM waveform. So whatever we generated now, similar AM signal will be passed to a detector. Okay. So we'll start with the square law detector. So again, for the square law detector, we are going to use the same square law modulator principle, and here also we are going to use a diode as a square law device. So here the input AM waveform is represented as V1 of t, and the output of the square law device is V2 of t. So this is again fed as input to a low pass filter. So with the cutoff frequency of FM. So we are going to ultimately have the message signal V0 of t. Only we are going to record the message signal here. So square law detector is obtained using a square law modulator. So input output relation for a nonlinear device is given by this equation. So we know that the square law modulator, so this is the relation between the input and the output. So the output V2 of t is given by A into V1 of t plus B into V1 square of t. So this is the general relationship nonlinear for the nonlinear device. So here we are going to pass the input AM waveform V1 of t, which is the AM waveform. So when nonlinear device is used for AM demodulation, the input signal is given as. So this is the input signal that is generated using our AM modulator. So we have the carrier waveform and the upper and the lower side bands. So here it is given as the product of the message and the carrier waveform. Substitute this second equation in the first equation. Let us simplify this second equation in terms of amplitude sensitivity. So here we are taking this term, that is the common term VC cos omega CT. It is common in first two terms. So it is taken outside. Okay. So this A term is also taken outside, so that we are dividing the second term by A. Okay, 2B by A. And this Vm into cos omega mt is represented as M of t. So this Vm cos omega mt is represented as M of t, and Vc cos omega ct is taken outside, and A. So since A is not there, we are dividing by A. So first term it's common. So it is 1 plus 2b by A into M of t. So this 2b by A, it's a constant term, which is amplitude sensitivity. It is K. So it is represented. This third equation is again represented as Vc cos omega ct 1 plus K into M of t. So this A is just neglected for simplicity. So you can take it as 1. So it's a constant term. Okay. So this amplitude sensitivity K equal to 2b by A. So this is the fourth equation where we have simplified the AM expression like this. Let us substitute fourth equation, which is the simplified version of the AM waveform in the first equation. Okay. And expand it. So now we substitute 4 and 1. Okay. So this is our fifth equation. After you simply substitute. So this A Vc cos omega Ct. So this A is there. V1 instead of V1, this Vc cos omega Ct into 1 plus K into M of t plus B into V1 square of t. So this entire term we are just squaring. Vc cos omega Ct into 1 plus K M of t whole square. Okay. So this first term you can take it inside, and the second term you have to use this 1 plus k m of t, we have to square it. Okay. So a plus b whole square form, just expand it. So now we are going to expand this. So this a vc cos omega ct into 1 plus k m of t plus b into this term is squared, vc square cos square omega ct into 1 square plus k square m square of t plus twice of k into m of t. So this is a plus b whole square form. So just we are using the formula and expanding. So after this, we have the sixth equation. Now further, we are going to simply expand this. To expand, this is again a vc cos omega ct into 1 plus km of t plus b into vc square. So this cos square omega t, again it is we are using this trigonometric identity. So half of 1 plus cos 2 omega ct. This is again seventh equation. The rest of the terms as it is. So then further we expand this. So this becomes our eighth equation. So this is again every term is taken inside. A vc cos omega ct plus a vc cos omega ct into k m of t plus b vc square half divided by 2, then plus b vc square cos 2 omega ct So this entire term is multiplied with the three terms here. So we are getting this equation. So just cross check this one. So this we'll get six terms totally. So totally eight terms. First two terms plus remaining six terms. Okay. Just expand and just check you're getting this eighth equation. Now this is passed to a low pass filter. So the low pass filter, we are going to recover only the message signal. Okay. So just find the terms where we have the message signal. So the second term we have the message m of t, right? And so here we have m square of t. In this fifth term we have m square of t. Sixth term also we have m square of t. So and the sixth term vc square k m of t, and the last term vc square k m of t. So we are going to have only the message signal, not the carrier one. So we are, after the low pass filter, it is going to filter only this term vc square k into m of t. After passing this eighth equation, the output of the uh, detector through to a low pass filter. So this is the desired term vc square into k into m of t, ninth equation. So this is in a low pass filter. So even though we have the other terms, it is going to be filtered. So we will have only this term message m of t. One more with m square of t. So you have this one, this fifth term, m square of t. So this is the undesired term. So we will take it for noise calculation. That is for SNR calculation. We are going to take this expression. So this fifth term, we will take it for the SNR calculation. The term half d vc square k square m square of t rise to a plurality of the similar frequency component. So this is we are just having the plural form, that is m square. We are having the m square term. So we calculate the signal to noise ratio. So we are taking this m square of t term as the unwanted term or the noise term. Okay. So the ratio of wanted signal to the distortion is given by SNR, signal to noise. So noise is taken something like a distorted waveform, distorted signal. So which is 1 by 2 b into vc square k square m square of t. So this fifth term we take it as the noise. So signal to noise is calculated as 2 by k into m of t. So if you just cancel the known terms, common terms, we have 2 by k into m of t. So this is SNR. So this is taken as a 10th equation. So we define this k into m of t as the modulation index. So this signal to noise ratio is inversely proportional to the modulation index. Okay. So if modulation index is low, then SNR is high. Or if the modulation index is high, then SNR will be less. Okay. So modulation index, we have to take care. So generally we define the SNR. Signal to noise ratio is defined as the ratio of the strength of the signal carrying information to that of the unwanted interference, or we can take some distorted wave. So SNR is greater than 1, then the message signal can be perfectly reconstructed by the filter. So if SNR will be high, then we can perfectly reconstruct at the demodulator side. So if SNR is less than 1, the message signal cannot be reconstructed back perfectly. So SNR should be generally high, and so we have to have a proper balance between the SNR and the modulation index. So this is one of the drawback here. As we have seen, signal to noise ratio at the input of the low pass filter is inversely proportional to the modulation index. So higher is the modulation index, then lower will be the signal to noise ratio. So to increase the signal to noise ratio, modulation index has to be decreased, which will decrease the modulation efficiency. So if you decrease M value, modulation efficiency will decrease. Therefore, we get inefficient power distribution. So this method is practically not preferred for AMD modulation. So this is one of the drawback when we use a square law detector. Okay. So that's why we generally prefer envelope detection when we do AMD modulation.